So, let us start with another topic in this week, which is called how efficiently we can calculate discrete Fourier transform. So, that is called fast Fourier transform. So, all the week, all the 6th week and 5th week and 6th week I describe about the discrete Fourier transform, their property, how they can be used, then we call about the DCT. Now, whatever the discrete Fourier transform of DCT, how can I compute it very fast? So, that is called fast Fourier transform algorithm. So, you cannot say the fast Fourier transform is an transform. It is an algorithm to efficiently compute discrete Fourier transform. So, you may say, why sir this is required? Why I require efficient algorithm? So, suppose I want to implement this discrete Fourier transform in a hardware. So, if as you know, the discrete Fourier transform of a signal, if it is xk one dimensional signal, then is n tends to n equal to 0 to capital N minus 1 x of n e to the power minus j 2 pi by n into nk, that we know. So, what is the complexity? I know this n square complex multiplication is required. So, if it is n square complex multiplication is required, that means it required 4 into n square real multiplication, and you know the multiplication is costly operation in hardware. So, if I want to implement DFT in a ASIC chip, let us say, so I write an algorithm which requires the computation of discrete Fourier transform and inverse discrete Fourier transform, because you know the discrete Fourier transform and inverse discrete Fourier transform both are required, because after that work in that domain you have to revert back the signal again in time domain. So, both the cases it has an n square complexity, n square complex multiplication. So, how do I reduce it? Reduction is very much essential for implementation in hardware. So, that much, how can I simplify that algorithm? There are a lot of computational simplification is coming out in the picture. As you know, suppose you have a long string, you know that, suppose I have a data from 1 to 1000. Now, I said find out it is haphazardly is there, find out that whether that 501 is there or not. So, I have to search for 501. You know, if it is linear search, that means the worst possible complexity is I have to search, compare each and every data with 501, and once I will find out. So, there is a worst possibility is that there will be a 1000 comparison I have to make. But again, you know, there is a lot of efficient algorithm is there. Simplest one is that binary search. If I divided the search, I divide and conquer. So, if I apply the divide rule, let us binary search means divided the entire sequence in a 2 sequence and the search for each of the sequence, then you know the complexity is reduced by order of log n, log 2 and n. So, if there is a 1000 search is required, now I required log 2 1000. So, that is obviously very reduced form. So, how do I make this computation, instead of n square multiplication, reduce the number of multiplication? That is the basic motto of fast Fourier transform algorithm. Okay? So, you just as I said, so if I say the DFT required n square complex multiplication, and in this lecture we always use Wn notation. Wn is nothing but a e to the power minus j 2 pi by n. which is written as Wn. So, instead of every time I write e to the power minus j 2 pi n k by n, I use the word Wn. Okay. So, that is the one thing. And next thing is that whatever the algorithm I want to do, I have to reduce this n square complex multiplication n 4 into n square real multiplication, because you know that x of n can be in the form of a plus jb, and you know e to the power j theta minus j theta is nothing but a cos theta minus j sin theta. So, it is again it is a let us say a1 minus jb1 form, a1 minus jb1 form. So, when I multiply these two things, xn multiply with this thing, what is required? I require one complex multiplication is equal to 4 real multiplication, because a will multiply with a1, a will multiply with b1, then b will multiply with a1 and b will multiply with b1. So, I require 4 real multiplication for a single complex multiplication. And if you see x of k varies from 0 to n minus 1. So, I can say I require a n number of multiplication for every k. Now, this side I require a n number of multiplication for 1 k. So, n number of k I require n cross n complex multiplication, that is nothing but a n square multiplication. So, I require 4n into n minus 1 real addition. Now, I want to reduce this complexity. Instead of n square, can it be make something which is less than n square? That is an efficient algorithm. So, depending on the algorithm, the efficiency of the algorithm, the computational complexity will be reduced. So, that is called fast Fourier transform. Then in what basis we want to improve what is the redundancy? You know that if I want to reduce the number of multiplication, that means some of the multiplication is may not required, but unnecessarily I am doing in here. So, I have to want to reduce that redundancy. How do I reduce that redundancy, and what are those redundancy? I want to know that. So, what is there? You know, discrete Fourier transform has a two property, symmetry property and periodicity property. So, if I say Wn e to the power minus j 2 pi by n, that has a two property, symmetry property and periodicity property. Symmetry property what? That if I know that at n by 2, the discrete Fourier transform spectrum is symmetry. So, I can say Wn k plus n by 2 is equal to nothing but a minus Wn k. We can prove it. What is Wn? What is Wn k plus n by 2 is nothing but a e to the power minus j 2 pi by n into k plus n by 2. I can say it is nothing but a e to the power minus j 2 pi by n into k into e to the power minus j 2 pi by n into n by 2. So, n cancel, 2 cancel. So, this is nothing but again Wn k. Now, what is e to the power minus j pi? E to the power minus j pi is nothing but a Wn k cos pi minus j sin pi. So, this portion is 0 and this is equal to minus 1. So, it is nothing but a minus Wn k. That is symmetry property. And what is periodicity property? You know that DFT transform is periodic at period of n, which is the length of the DFT. So, Wn again Wn to the power k, Wn k plus n is nothing but a Wn k, because it is periodic, because it become cos of 2 pi minus j sin 2 pi. So cos of 2 pi is equal to 1 and minus j sin 2 pi equal to 0, so it is 1, so it will becomes Wnk. So while I am computing DFT k equal to 0 to n minus 1, I know that k equal to 0 to n minus 1, there is a symmetry and there is a periodicity property. So can I exploit these two property to reduce the computational complexity of discrete Fourier transform? So when I directly compute DFT, we are not using this, we compute all x of k, but it may not be required. So using that redundancy information, can I do that? So that is called fast Fourier transform algorithm. So how I use that? So the goal, that what is the goal of the algorithm, whatever the algorithm, fast Fourier transform algorithm, that means efficient computation of discrete Fourier transform. The goal is the total number of computations should be linear rather than quadratic. If I say n square is n quadratic, so instead of n square, can I make it n into something a or something b which is less than n? So instead of square, I make it linear, a into n or b into n, where the a and b are both are less than n. So instead of n square, I want something which is nothing but a into n. So a is less than capital N, then my algorithm required less number of multiplication compared to the direct computation of DFT. Okay. So most of the computation can be eliminated using the symmetry and periodicity property. So I use those two property to make it a into n. How do I make it? It is called adopt a divide and conquer approach to reduce the computation. I now use divide and conquer approach to reduce the computation. So that is the goal of my fast Fourier transform algorithm. If you see, the FFT is not unique, many algorithms are available. So FFT is not a transform, fast Fourier transform algorithm. It is an algorithm to efficiently compute discrete Fourier transform. Discrete Fourier transform is a transform. Fast Fourier transform is an algorithm to implement discrete Fourier transform in efficient manner. Then the algorithm may not be unique. There may be many algorithms, and all algorithms may not be the same computationally, that you can say the simplification is done. So maybe algorithm 1 is less computational complex compared to the algorithm 2, but there may be some merits and demerits of each of the algorithms. Not only reduction of the computational complexity, there may be other artifacts, like that input required shuffled, output will come with shuffled. Sometime I require and you can say that some kind of arrangement of the signal, some kind of arrangement of the output. So lot of merits and demerits will come. So how the input will be arranged, how we so I have said divide and conquer approach. How do I divide? Should I divide that entire sequence in a 2 sequence, or should I divide it in a 4 sequence? Should I divide it in a n sequence? So how do I divide? How do I compute? So that depending on that approach, different FFT algorithms are available, and every algorithm has its own merits and demerits. So again I am saying, the purpose for fast Fourier transform is efficiently compute discrete Fourier transform. So FFT not a new transform, it is an algorithm which is computationally efficient to compute DFT utilizing the properties of DFT. One is symmetry, another is periodicity. Let us say compute n-point DFT using divide and conquer approach. So, I divide, let us say I have to compute n-point DFT. So, this DFT length is n and n is equal to, I have divided n. So, n is equal to L into m. That means, suppose I have n equal to, let us say 200. I can say that 200 is nothing but a, let us say 50 divided by 50 means 50 into 40. So, I can say L is equal to 50 and m is equal to 40. So, if I say 40 n is equal to 50 into 40, again it is 200. Sorry, not 40, 4, 50 into 4, sorry, 50 into 4. If it is 2000, then I can say 50 into 40, let us say 2000. So, 50 into 40, again it is 2000. So, length of the DFT is not a prime number. When I directly compute DFT for n-point DFT, n is equal to m into L or L into m, whatever, where the m is equal to n and L is equal to 1, or L is equal to n, m is equal to 1. So, except n is a prime number, so if my length of the DFT is not a prime number, then I can use the divide and conquer approach. So, when you go for the divide and conquer approach, the first criteria is that n must be a not prime number, n cannot be a prime number. If it is prime number, then I cannot apply the divide and conquer rule. So, if it is a non-prime number, or it can be expressed in a product of two numbers, then I can divide the n sequence in a two part. One is m, another is L. Now, suppose I have an x of n, which is n number of samples are there, n number of samples are there. How the signal is stored? So, let us, there is an array, here is stored x0, this location is stored x1, this location is stored x2, like that up to x of n minus 1. X of n minus 1 number of samples are stored. Now, I said that n can be divided, n is a non-prime number and can be expressed as an m into L. Now, instead of storing the signal in a single array, can I store in a two-dimensional array, which is here? Can I store the data in a two-dimensional array? This axis is L and this axis is M. So, how do I store it? I have an n number of sample. So, I said first m number of sample are occupy the first row. So, 0th sample to m minus 1 number of sample is occupy the first row. Then m sample to 2m minus 1 number of sample is occupy the second row, and that way up to xn sample. So, if n is equal to m into L, then I can say that there will be a L number of row required to store the n number of sample. For example, suppose I have an xn or n is equal to, let us say 100, and I express, so I can store 100, let us say n is equal to, I have divide it into, let us say 20 into 5. So, m is equal to 20 and L is equal to 5. So, 0 to 19 sample will be occupy the first row then 20 to 39 sample occupy the second row, then 40 to again 20 sample, 40 to 59 sample will be occupy the third row, and then 60 to 79 sample, then I can say 80 to 100 sample. 100, not 100 sample, it start from 0, so it is 99 sample. So this is 20 sample, so there will be a 20 column and 5 rows. So number of rows is defined by L and number of column is defined by M. When I store the data in row wise, now same thing can be done in column wise also. I said I will store the data column wise. So M is equal to ML. Now I said M is equal to 5, L is equal to 20. So I can say 0 to 19 sample will store in first column, and then 20 to 39 sample will be stored in second column, that way. So how many columns will be there? 5 columns will be there. So both are possible. So if I want to store n number of data in a two-dimensional array, so instead of x of n, I said x of L and M. Index is changed to L, M, N. L is the whatever, L is the number of column and M is the number of rows. So M is the number of column, L is the number of rows. Whatever you can say. I can store the data row wise or I can store the data column wise. Both are possible. So let us say my mapping is n is equal to ml plus small m. So I am storing the data in row wise, then n is equal to m into L plus m. M is varies from 0 to m minus 1 and a small l is varies from 0 to L minus 1. You can see that when that L is equal to 0, m is varies from for every L. So for L equal to 0, n equal to 0 plus m. So from 0 to m minus 1. Then when L equal to 1, then n equal to, I know, m equal to 1 means m into 1. So m into 1 2 plus m. So first we will start from xm, then we will start from x capital M plus 1, then we will start from capital M plus 2 up to capital 2m minus 1. So I store the data row wise. Then my mapping index is n is equal to m into L plus m. So there is a m number of column and L number of rows. Okay. Now I said no, I want to store the data column wise. Then what will be the index? N is equal to L plus Lm. Just reverse. N is equal to small l plus capital L into m, small m. So when for m equal to 0, n is equal to L. L is varies from 0 to L minus 1. And when small m is equal to 1, n equal to small l plus capital L. So it will start from, so I store 0 to L minus 1 in first column, then L to L minus 1 in second column, third column, fourth column, like that way. So when I store the data in column wise in a two-dimensional array, then my index is n is equal to L plus capital L into M. When I want to store the data in row wise, then n is equal to capital M small l plus m. Is it clear? So, I have an one dimensional data that can be mapped in a two dimensional array. So, my new xn is not x of n, it is x of Lm. Now, if my x is x of Lm, then xk is not x of k, xk will be x of p and q. Okay or not? So, now that x of n, when it is expressed in a x of n single dimensional array, then I get x of k. Now, I have an x of Lm two dimensional single dimensional signal make an image two dimensional array. Now, I should have an x two dimension p and q, L and m both the dimension will be there. So, transform domain also there will be a both the dimension, it is not only xk, it will be xp and q. Again I can say that if k equal to mp plus q, so p is varies from 0 to m and q is varies from 0 to L. So, if it is mp plus q, that means output is stored in row wise, and when is k equal to p plus ql, output is stored in column wise. Sorry, q, this will be q is varies from 0 to m minus and p is varies from 0 to L. Because if you see here L plus Lm, so same thing here also L plus p plus ql. Okay. So, I can say that xk is also stored in row wise or column wise, both are possible. Now, if it is that things that sk is stored in row wise or xk is stored in column wise, then what is the DFT? So, this is my DFT equation. So, let us say I will take another slide here. So, I have an x of n, instead of x of n I get x of Lm, then I have an x of k, instead of that I get a capital X of p and q. Now, what is x of n? X of what is capital X of k is nothing but a discrete Fourier transform n equal to 0 to n minus 1 x of n w n n k. That is my discrete Fourier transform. Now, what is x of p and q? So, there is a two dimension, one is p dimension, another is q dimension. So, if you see that m small m is equal to, not here small m, let us p is equal to 0 to m minus 1 and sorry, this will be m. So, m is okay, let us come in here. So, I have an p and q in k is divided. So, xk is store p and q array and my x of n is store L and m array. So, n is expressed in term of L and m. So, n can be, let us say L is equal to 0 to or m is equal to 0 to n m capital M minus 1, then L is equal to 0 to n minus 1 x of Lm into W n. Instead of n, I said how I represent n here. How I represent n here? I can say, if I say m is so there is a okay, there is a two for loop. Okay, let us start freshly again. So, what I said, I have an capital X PQ is equal to now capital X PQ. So, x of k is equal to n equal to 0 to n minus 1 x of n w n n k n point DFT. So, capital X PQ. So, I have said the n is divided in term of m into L. Now, let us say the data is stored in column wise. Data is stored in column wise. So, the data will go like this, then again come back here and go like this. Data is stored like this. So, what is the mapping function? I know n is equal to L plus m into L plus capital L into m, small m. Capital L into small m. Why? That means I am computing column wise. So, first for loop will start from 0 to L minus 1 for every m, and second for loop. First for loop start from m equal to 0 to capital M minus 1. So, for every m I am calculating L minus 1. So, I can say that inner loop, let us say I write in here x of PQ, inner sum will be come from L equal to 0 to L minus 1, and outer sum will come from m equal to 0 to m minus 1, because the data is stored in a column wise and the mapping function is n is equal to L plus capital L into m. Okay. So, now I have an x of Lm or ml, whatever, e to the power or wn. So, instead of n I have an L plus capital L into small m. Now, if it is computed in column wise, that it can be shown that when I get the output, it will be stored in row wise. So, if it is row wise, what is that? What is that? Row wise is n equal to ml plus m. So, here it is not n, it is the index k. So, index k has to be stored in row wise. So, how the index k is stored in a row wise? That is nothing but a k equal to, so it is this mapping is row wise, this mapping is column wise. So, k is equal to mp plus q. So, I can say here I can write k is equal to m into p plus q. Have you understand or not? I said I store the data in column wise, there is a m number of column. So, the mapping function is L plus a capital L into m. Now, I said the output, the computed output xpq is stored in row wise. So, I get k index in term of mp plus q. Both L, M, P, Q, L is varies from 0 to capital L minus 1, P is varies from 0 to capital L minus 1, and Q is varies from 0 to M minus 1. Is it clear? So, now I get this equation. Okay. So, M equal to 0 to M minus 1, L equal to 0 to capital L minus 1, this one. Now, if I see, so I can say I have a 4 Wn product, Wn L into MP. So, W small l MP, this one is 1, then small l and q, small l and q. So, I get small l and q. So, this is this Wn L multiply with MP, this one, then L multiply with Q, this one, then Lm multiply with Mp. So Lm Mp, and then Lm will multiply with Q. So Lm Q. So those are 4 Wn I will get. Now say Wn Lmp, Wl Lmp. So Wn Lm small m capital MP is nothing but a Lm Mp. So what is Lm? Lm is nothing but a n. So Wn, okay. So Wn n Np is nothing but a Np. Mp. So it is small m and p. Small m and p both are integer. So Wn to the power any integer is nothing but a 1. Wn n Mp, which is nothing but a e to the power minus j 2 pi by n into n Mp. So n cancel. So it is nothing but a minus j 2 pi Mp. M and p are integer. So if it is an integer, product is also an integer. So it is nothing but a cos 2 pi minus j sin 2 pi. So minus j sin 2 pi is 0. N into or p into minus j sin 2 pi. So it's nothing but a 0, and this one is 1. So this is nothing but a 1. Then what is Wn L capital MP? Wn L capital MP. So I can express in terms of WLP n by m, because e to the power minus j 2 pi by n into m LP. I can say it is nothing but m, it can be written in here also. So if it is e to the power minus j 2 pi by n, then I said Wn. Now if it instead of n, it is n by m. So instead of n, I can write n by m. So that's why I write n by m. So what is n by m? N is nothing but a ml. So it is nothing but a l. So that's why WL to the power LP. Similarly, WNL LMQ, same thing, vice versa. Only WLQ and LQ will be remain same. So now we simplify this one and let's we see what we will get. So in the next lecture, I will show you that how it will be simplified. Okay? Thank you.